Hey everyone, and welcome back to The Explainer. Honestly, huge congratulations are in order here. You've officially powered through and conquered all the major concepts of Chapter 3. I mean, think about it. We've already tackled Part 1 with the physical properties, Part 2 on the chemical properties of metals, Part 3 covering nonmetals and ionic compounds, and Part 4, which dove into extraction and corrosion. Now, we're bringing the whole shebang together. This is Part 5. It's a high-energy, complete revision bootcamp designed to lock in those crucial concepts so you can absolutely crush your upcoming board exams. Let's do this. So here's our quick roadmap for today's masterclass. We're going to hit 6 key areas: metals versus nonmetals, chemical properties and reactivity, forming strong ionic bonds, extraction, alloys and ores, the battle against corrosion, and then we'll wrap up with an essential exam question review to make sure you're totally ready for whatever they throw at you.
All right, let's jump right into Section 1, metals versus nonmetals.
To really master this chapter, we first need to put these two heavyweights head-to-head. On one side, we've got metals like iron, copper, and gold. These guys have luster, meaning they're super shiny. They're tough, they're malleable, so you can pound them into thin sheets like aluminum foil, and they're ductile, meaning you can stretch them out into copper wires. Plus, they are fantastic conductors of heat and electricity, and they're sonorous, so they ring out just like a school bell. Now, on the exact opposite side, we have nonmetals like oxygen and carbon. These are basically the anti-metals. They lack luster, they break instead of bending, so no malleability or ductility there, and they're pretty terrible conductors. Juxtaposing these classic traits is honestly the best way to lock them into your memory. But wait, you know examiners absolutely love a good plot twist, right? Enter the rule breakers. These exceptions are a huge deal. Take graphite. It's a nonmetal, yet it conducts electricity beautifully. Then there's iodine, another nonmetal, but it has a really distinct shiny luster. And you can't forget about sodium and potassium. These are technically metals, but they are so incredibly soft that you could literally slice them with a butter knife. Definitely keep a mental star next to these exceptions. Moving right along to Section 2, chemical properties and reactivity. Let's look at how these elements actually behave out in the wild. When metals react with oxygen, they form basic metal oxides. But when nonmetals react with oxygen, they form acidic oxides. It's a nice and neat divide. Also, if you drop highly reactive metal into water or an acid, boom, you're going to generate hydrogen gas. Now, the absolute crucial thing to remember here is the existence of amphoteric oxides. Elements like aluminium and zinc form oxides that basically play for both teams. They can react with both acids and bases. That little fact is a major exam favorite. Next up is the reactivity series. Think of this as the VIP hierarchy of elements. We rank them starting from the most highly reactive, kind of volatile metals at the very top, so potassium and sodium. Then we work our way down the ladder through calcium, magnesium, aluminum, zinc, iron, and lead. Then we hit hydrogen, which serves as our baseline. Below hydrogen are the much lazier, more relaxed metals: copper, mercury, silver, and finally, sitting completely unbothered at the very bottom is gold. Understanding this specific order is the absolute key to predicting any displacement reaction. All right, Section 3, forming strong ionic bonds. Think of an ionic bond as the ultimate chemical trade agreement. Metals usually have extra electrons that they desperately want to get rid of, and nonmetals are more than happy to snatch them right up. When the metal gives away an electron, it becomes positively charged. The nonmetal gains that electron and becomes negative. Opposites attract, right? So this really powerful electrostatic force completely locks them together. The most famous example, which you probably have sitting in your kitchen right now, is sodium chloride, also known as table salt. Now, how does this invisible trade agreement affect the physical world? Well, because that ionic bond is incredibly tight, separating those ions takes a massive amount of energy. That's exactly why ionic compounds are rock-hard, brittle, and have exceptionally high melting and boiling points. They dissolve easily in water, but here is the trickiest property. As solids, they are actually insulators. They only conduct electricity in a molten or aqueous state. Why? Well, because melting them or dissolving them finally breaks that rigid structure, freeing up those locked ions to move around and carry an electrical current. Time for Section 4, extraction, alloys, and ores. First, let's clear up a classic point of confusion. Minerals are simply naturally occurring substances that you find out there in the Earth's crust. Ores, however, are the VIP minerals. They are the specific minerals from which we can extract a metal economically and profitably. So, repeat this catchy phrase with me, because examiners love to test it. All ores are minerals, but all minerals are not ores. Getting that shiny, pure metal out of a dirty rock requires a 4-step magic trick called metallurgy. Step 1 is the concentration of the ore, which is basically just washing off the useless dirt and sand. Step 2 is roasting, or calcination, where we heat it up to convert the ore into a metal oxide. Step 3 is reduction, where we chemically strip away that oxygen to leave just the metal behind. And finally, step 4 is refining, where we polish it up to get pure, 100% usable metal.
But, sometimes a pure metal just isn't tough enough for what we need it to do. That's where alloys come in. An alloy is a homogeneous mixture. It's basically the ultimate material upgrade. By mixing different metals together, we create super materials. Mix copper and zinc together, and you get brass. Combine copper and tin, and you get bronze. Or if you mix iron with a little chromium and nickel, you get stainless steel, which is amazing because it powerfully resists rusting.
And speaking of rusting, that brings us to Section 5, the battle against corrosion. Corrosion is the gradual, completely silent destruction of metals caused by the environment around them, specifically air, moisture, or chemicals. The absolute classic example here is the rusting of iron. For your exams, you need to know exactly what rust is on a chemical level. It's hydrated iron oxide. It's essentially what happens when iron loses a slow battle against oxygen and water. But we definitely don't just sit back and let our metals turn to dust. We use several everyday tactics to build a protective barrier between the metal and those harsh elements. Simply painting, oiling, or greasing the surface works wonders. We also use alloying, like we just talked about, to change the chemical makeup entirely. And this brilliantly illustrates our absolute premier defense strategy: galvanization. This is the process of coating iron with a very thin, protective layer of zinc. That zinc layer acts as a sacrificial shield, completely blocking air and moisture from ever reaching the vulnerable iron underneath. Make sure you highlight galvanization in your notes, because it is a very frequent, high-value, long-answer question.
Finally, we've made it to Section 6, Essential Exam Question Review. Okay, we're kicking this off with a rapid-fire one-mark gauntlet. You ready? First, which metal is so reactive it actually has to be stored in kerosene? Second, name a non-metal that breaks the rules and conducts electricity. And third, thinking back to our hierarchy, which metal is the absolute least reactive?
Let's see how you did. Did you say sodium and potassium for the first one? They are wildly reactive and have to be kept safe in kerosene. Next, graphite is our rule-breaking non-metal that conducts electricity. And gold is the least reactive metal, chilling safely at the very bottom of the series. If you nailed those, your memory of the exceptions is looking great. Let's step it up a notch with 2 classic, slightly deeper conceptual questions. For 2 marks, why are ionic compounds good conductors only in a molten state? And then, considering all the amazing metals we have to choose from, why do we specifically use aluminum in overhead electrical cables?
Here is the exact logic you need to write down for your exams. For that first question, in a solid state, the ions are locked tightly together. But when they enter a molten state, that rigid structure breaks down entirely, and the ions become free to move around and actually conduct electricity. For the second question, aluminum is the go-to choice because it perfectly balances being a fantastic conductor with being incredibly lightweight. If we used heavy copper wires up there, they would just drag the cables down.
And there you have it. You have officially revised the entire chapter and are thoroughly prepared to crush your board exams. But before we sign off, I want to leave you with one final provocative thought. Take your eyes off the screen for just a second and look around the room you're sitting in right now. Can you actually identify the specific metals, non-metals, and alloys that you are relying on every single day? From the copper wires hidden inside your walls, to the stainless steel out in your kitchen, to the glass and plastics totally surrounding you. Chemistry isn't just a bunch of facts you memorize from a textbook. It literally builds the world you live in. Thanks so much for joining me for this explainer. Stay curious and keep learning.